We're going to be simplifying some square roots. We'll start with the rational ones, but then we'll work more on simplifying irrational square roots. First of all, let's figure out what the heck a square root is. Square roots are the inverse of squares. What I mean by a square is that's another name for a exponent of 2 or a power of 2. So if you multiply a number by itself twice, that gives us a power of 2. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and so on. The result here you get are what are called perfect squares. A whole number squared gives us the result of a perfect square. A square root is how we work backwards. So if we want to undo this perfect square and get back to where we started, we need to square root it. So notice that if I do 3 squared, I get 9. And if I square root 9, I get back to 3. So here we can just see that we're working backwards from this list or these columns right here. Another example might be, what's 8 squared? 8 squared is 64. So the square root of 64 must be 8. So practicing and getting better at recognizing these is pretty essential to doing the next step. However, if you need to refer to this list, of course, keep it handy. As I said, squares and square roots are inverses. We may think that that means that they're the opposite, but in math, we can't think that way. Opposite means something different in math. We call these inverses. These are operations that undo each other or cancel each other. So for example, if I take the square root of some number squared, well, the square root and the exponent of 2 cancel each other, and we're just left with the value. Another way to think about that is the square root of a number and then squaring that. So this time the exponent of 2 is outside the radical. Doesn't matter, they still undo each other. So this power of 2 and this square root are going to cancel each other, just leaving behind that value underneath. Let's just practice that concept real quick and some different ways that we can visualize it. Here we have the square root of 13 squared. 13 squared, another way to think about that is 13 times 13, and 13 times 13 is 169. If you square root 169 on your calculator, it should tell you the result is 13. So there's no reason to go through this process if you understand this idea that squares and square roots cancel each other and we're just left with the number there. Second example, this time the square or exponent of 2 is outside the radical. That doesn't matter. They're still going to cancel each other. But another way that we can think about it instead of that is squaring a number means multiply it by itself. So I'm going to multiply the square root of 8 times the square root of 8. That means that I can multiply 8 times 8 under 1 square root, and I'll show you the property that that comes from in a minute here. 8 times 8 is 64. You could square root 64 on your calculator. It'll tell you it's 8. Or we can take those pair of 8s that are being multiplied, rewrite that using a square, and here we see the exact same thing we happened over here, where squaring a square root undoes itself, and we're just left with that number. One way to make it slightly more complicated is to put a number in front of your square root or radical symbol there. If that happens, well, we're just squaring that number as well. Be careful not to think that we're distributing this exponent. I mean, in this case, it's okay to think that way, but as you advance in math and you start having other operations in between here, like plus or minus, we are not allowed to distribute the exponent. So another way that you would think about it maybe is rewriting it twice, multiplying it by itself, and then just multiplying your pieces together. So the 2's at the front can get multiplied and get 4. And the square root of 5 times the square root of 5, you could write as the square root of 25, multiplying those 5's together. Or you could think about it as 5 squared under the radical. Either way, the square and the square root are going to cancel. The square root of 5 times the square root of 5 is just 5. So this is really just 4 times 5, which equals 20. And the more you get used to squaring values that look like this, maybe you can take the shortcut of just squaring the front value and then multiplying by the value under the radical, because the square root is going to get canceled. So the square root of 2 times 5, or 4 times 5, is 20. Eventually, in our next lesson, we're going to see values like this on a right triangle, and we're going to have to use the Pythagorean theorem. So we're going to be squaring values that look like this. So we need to practice doing that so that we can be ready for the next lesson. All right, we talked about what are called rational radicals. A rational radical is where the radical is simplified into just a nice whole number. So in this video, we're just strictly looking at squares and square roots, although we could have perfect cubes, we could have perfect fourths, perfect fifths, and so on. But again, we're just focused on our perfect squares here. So here we have a list of our perfect squares. We're going to need that as our reference here, because what we're going to do is we're going to simplify what are called irrational radicals. Now, irrational radicals are not going to give us these nice whole numbers when we take the square root. They're going to give us ugly decimals that never end or never repeat. For example, the square root of 2 is a good example of an irrational square root. On your calculator, if you do the square root of 2, you'll notice that it gives you a decimal value. And it can only give you as many values as the screen size allows, but if it could go on forever, it would. And so the reason that we like to use square roots, or roots in general, is because they allow us to contain those infinite amount of decimal values into one nice little symbol. So we can work accurately with irrational numbers. All right, I hinted at a product property that I was using right here, taking these two square roots and just multiplying the two numbers under one square root, and that is what this property allows us to do. I can take two numbers that have separate square roots, or as long as they have the same root, I'm allowed to do this. And I can move those two numbers under one square root and multiply them together. Or I could work the other way. Maybe I want to factor a number, and this is what we'll do in the next couple of steps here. If I factor a number into two numbers that multiply, then I can break those two numbers up and give them each their own individual radical. And so we're going to be able to do that. What we're going to want to do is use a perfect square factor. So when I break up a number into two numbers, one of those numbers I want to be a perfect square. Again, one of these numbers right here. Typically, we only need to use 4, 9, 16, or 25. Occasionally, we may need to use 36 or 49, and maybe even higher ones if we get really big numbers. But typically, those first four right here, 4, 9, 16, and 25, tend to do the trick most of the time. There's what we want to divide numbers by or factor them by, and then we'll be able to break it apart and square root those numbers into nice whole numbers, but they'll leave behind another number in the radical. So let's see what happens here. For example, the square root of 12 is an irrational square root. Its value is a decimal, but what we can do is we can simplify by factoring out a perfect square factor, because 4 times 3 is 12. If we give 4 its own square root, then we're allowed to simplify that. The square root of 4 is 2, and then 3 stayed behind under the radical. So this is the simplified version of the square root of 12. Not a different value, just a different way of looking at it. All right, square root of 27. Again, we're trying to divide by 4, 9, 16, or 25. As it turns out, 27 can be divided by 9, or factored into 9 times 3. We can separate those two numbers now, give each their own radical. The square root of 9 can be simplified to 3, And this 3 stayed behind under the radical. So there's our simplified version of the square root of 27. All right, one more time, and just to throw an extra thing in there to complicate it, we got this number sitting out front. All these values are being multiplied here. So any number that gets simplified out into the front is going to get multiplied by that number in front that's already there. So let's ignore that 2, but let's not forget it in our steps. Let's just focus on simplifying the square root of 32. So we go back, use our perfect squares here. Can we divide it by 4? Yes, 8 times 4 is 32, but let's check and see if we can find a bigger one, because if we can find a bigger perfect square factor, then we can do it in less steps. Try and divide it by 9, that doesn't work. We can divide it by 16. 16 times 2 is a factor pair of 32. So let's break those up, give 16 and 2 their own square roots. Simplify the square root of 16, and we get 4. Now we can bring that 2 back into play and multiply it by the 4 there. And we get 8 at the front. This 2 stayed behind under the radical the entire time and was never allowed to get out. So our final simplified answer is 8 times the square root of 2. All right, so there's just a couple examples of how we can simplify square roots. You've definitely got a practice worksheet to continue practicing that. This is an important skill that we're going to need in this unit, as we are going to be using values that contain irrational square roots, and we're going to be able to simplify our answers when we're working. All right, so definitely continue to practice simplifying those perfect squares, using perfect squares. Simplify your irrational square roots using perfect squares.